Dear students, welcome to this session. In this session, we are going to talk about the process creation. The virtual memory, it allows a great benefit in terms of process creation. As we know, all the pages are not loaded during the process creation. So, the additional overhead has been reduced in the process creation. So, process creation is more efficient. So we'll look into the copy on write and memory mapped files. Copy on write. When a process is created, we know the system call fork. The fork is used to create the child process. Whenever the child process is created, it will share the address space of the parent. Copy on write allows both parent and the child process to initially share the same pages in the memory. Copy on write, what it will do is it will share the both the parent and child will share the same memory space. If either process modified a shared page, only then is the page copied. So here what the technique is used, if any of the parent or the child process who are sharing the pages, if any one process modifies any page, a copy of that page is made only when certain page is changed. Copy on write allows more efficient process creation as only modified pages are copied. So only the modified pages are copied. Otherwise, if any page is just used for the reference, it will have only one copy. But if any child or the parent process modifies any particular page, one additional copy is made for the modified, whatever the changes are there, additional copy will be made. Free pages are allocated from the pool of zeroed out pages. So whatever the free pages that are required, it will be allocated from the pool. Page replacement. What is a page replacement? In the earlier discussion, we looked into what is a page fault. The page fault is whenever a certain process has an instruction that refers to a page and that particular page is not on the memory, that is when page fault occurs. When page fault occurs, what happens? Operating system will look for that particular how we get the page fault whenever that particular page is not present in the page table. So when it is not present in the page table, it will be as a invalid reference. When it is an invalid reference, operating system will check whether it is a invalid reference of the memory or it is because of the page being not present in the memory. That decision is made by the particular operating system, and if it is a invalid memory access, then error is generated and the process is aborted. If the particular page is valid and it is not present in the main memory, operating system will look in the disk or the secondary memory, and it will free up certain frame and it will load that page. That particular page replacement, that is called as a page replacement. Operating system bringing that page from the disk on top of the main memory and updating the page table, and how which page will be replaced, it depends. So one thing is a good case scenario is if there are free frames available, then there is no problem. The whatever the page is requested by the process will be loaded onto the free frames, and accordingly the page table will be updated. Let us say the frame is full and there is no available space in the frame, then what it will do is it will use a page replacement algorithm. So we will see what are the different page replacement algorithm, and using that it will find a victim page and it will swap out that particular page and it will swap in the required page which is required by the particular process which caused the page fault. So this whole process is called as a page replacement, and there are different algorithms for page replacement. Page replacement prevent over allocation of the memory by modifying page fault service routine to include page replacement. So using this technique, we are preventing over allocation of the memory. We are not loading all the pages. Whenever the page is requested, on demand we are going and getting the required page from the disk and loading onto the memory. And use modify or dirty bit to reduce overhead of page transfers. Only modified pages are returned to disk. Okay, so when we do the page replacement, we talked about the earlier scenario where we for particular instruction wanted to access a page. That page is not available in the memory. Operating system looks for that particular page on the disk, and when it finds the particular page, then it will look for the free frame where it can load that particular page. If that frame is not having a available free frames, then what it has to do is it has to identify, based on the replacement algorithm, it will identify the victim page and it will swap out the victim page. Okay, it will take that page to the disk, and it will swap in the particular page which is required. So if you see, there are two transfer. Okay, there is a overhead of page transfer. One is we have to swap out one page from the frame to the disk, and another one is from the disk to the frame. So there is a additional overhead. What we can do is we can use in the page table additional bit, we call it as either modify or a dirty bit. Using this bit, we can reduce that overhead of page transform to certain extent. So what is the technique used here is the page bit will be set only if there is a modification to that particular page, otherwise it will be set as 0. Means suppose if particular page is accessed by the a certain process and that particular page has been modified, then the dirty bit is set or the modify bit is set, otherwise it is not set. You can think it as, if there is any modification, this bit is set to 1, otherwise 0. And when we are doing the let us say we are operating system is doing the swap out, then it will look for the page which is not dirty or which is not modified. In that case, if it particular page is not modified, we need not copy it onto the disk. Okay, just we can bring out the new page and we can replace it on top of the frame that is used as a replacement. So we are avoiding one transfer, that is from the main memory to the disk. Only when if there is a we operating system or the replacement algorithm does not find a particular page which is not dirty or which is not modified, then only there is a need for copying that particular page onto the disk, and whatever page we want to load from the disk to the main memory, there will be two transfers. Otherwise, if you find a page which is not modified, there is only one transfer, that is from the disk to the main memory. Page replacement completes separation between logical memory and the physical memory. So the page replacement gives a clear separation between the logical memory and the physical memory. So this is also a great advantage. Because of this separation, large virtual memory can be provided on a smaller physical memory. So this is the advantage, like the processes that we are running, it is not restricted to the size of the physical memory, because we can have a larger virtual memories. So what is the need for the page replacement? The need for the page replacement, whenever there is a page fault, means a required page is not available on the main memory, that time that particular page has to be loaded from the disk. So that is why we need a page replacement. So you can see an example here. This particular process, okay, uh, logical memory for the user 1, and we have another process, logical memory for user 2. So these are the two different processes, and they are requesting various pages. Program counter, you can see here, load m. So m page is required, and if you see the whenever there is a requirement of the page, the page table is looked up. So this is the page table for this process, and this is the page table for this process. The page table is looked up, and this page table is indexed by the page number that we already know. So what is the index of this? 0 1, and for that it is a valid bit, and frame number 4 is assigned for that is the mapping. At the frame number 4, it finds the page, this particular page. That is how it will use the that particular page. It need not go to the disk, it will get that particular page on the memory. In the second process, you can see here, there is a request for the page B, and the index location is 1, and you can see at index location 1 it is invalid. If it is invalid, then operating system has to load this particular page. So what it will do is, it will check for the secondary memory, it will check the disk, it will get that particular, it will identify the particular page, and it will load that particular page into the memory. First it will load, it will find a free frame, and it will load it. If it doesn't find a free frame, then it will use the page replacement algorithm. So page replacement algorithm can be a FIFO or LRU or any other technique. We will see it in a little bit. Using any of those technique, it will load that particular page onto the memory, and it will be loaded on particular frame. And once it loads that frame number is mapped here, and this bit is changed to valid, and that particular instruction which requested the page B will be restarted. So when it restarts, it will find a mapping for that page, because that page is loaded, and that is how the process will continue. So basic page replacement. How the page replacement is done? First is find the location of the desired page on the disk. So whatever the page has been requested by the process, that is located on the disk. Then second step is find a free frame, because we need to load it onto the memory. First we have to find a free frame where we can load this particular page. If there is a free frame, use it. If there is a no free frame, use a page replacement algorithm to select a victim frame. So if we have a free frames, there is no problem. This desired page is replaced onto that frame, and accordingly page table will be updated. If the free frame is not available, using a page replacement algorithm, we have to find which particular page among those frame has to be as selected for the swap out. We call it as a victim frame, and it will select the victim frame, and it will swap it out of the memory. And next step is read the desired page into the newly free frame, update the page table and frame tables. So whatever the victim is selected, victim will be swapped out, and in that particular frame desired page is loaded. Okay, and then we update the page table as well as the frame tables with the new information. Then we restart the process where we got the page fault. So this is the how the page replacement is done. You can see here, this is the page table, and in this page table there is a request for the certain page, and this particular page request, it finds it as a invalid. So invalid means it has to, this is not available on the physical memory, it has to be loaded from the disk. And first it will identify the page on the disk. So this is the page. First what it will do is it will swap out the victim page. It will take out this victim page out. This victim page, how it is selected based on the replacement algorithm, it is swapped out and then changed to invalid, because earlier this victim frame will be having it as a valid. Once we move out, first thing we have to do is make it as a invalid, change that valid invalid bit to invalid. Then the reason being, if any other process tries to access this page, should not be able to find that particular page, because that particular page has been swapped out. Once we have changed that to invalid, then whatever is the desired page is loaded back onto the memory, and once it is loaded back onto the memory, we reset the page table for the new page. So whatever the new page we got it, we will update the page table with that particular information. Page replacement algorithms want lowest page fault rate. So how the page replacement algorithm should be? We would like to have the lowest page fault rate. What is the lowest page fault rate means? We don't want to have too many page faults, right? The algorithm should be designed in such a way that the number of page fault rate means what? Number of faults occurring should be minimal. The reason being, whenever there is a page fault, there is an additional overhead of the page replacement. So if the algorithm reduces number of the page fault, then the access time will be reduced and the process execution will be faster. Evaluate algorithm by running it on a particular string of memory references and computing the number of page faults on the string. So how we evaluate the algorithm? What is the evaluation of the algorithm is? We have to check how well the particular algorithm, whatever the algorithm we select, how well it will work. So for that we will consider a string of memory references. So this is the memory reference we are going to use when we are discussing about the algorithm. So what is this reference string is? This is the order in which the pages are requested. So here you can see the page number 1 is requested, after that 2 is requested, 3, 4 and so on. So we will take some reference string and we will evaluate all the algorithms based on this particular reference string, how well it will do on that particular string. The basic requirement is what? We want to have a lowest page fault rate. And also the number, see on the x-axis you have number of frames, and on the y-axis you have number of page faults. You can see here the number of page faults. Here for example, the number of frame is 1. When number of frame is 1, the page fault is very high. Okay, so this is not desirable. You can see as the number of frames are increasing, the page fault is reducing. For example, when we increase the number of frames from 1 to 2, the page faults, which is almost here close to 12, has been reduced to close to 7. So as we keep on increasing the number of frames, okay, the page faults will reduce. So this gives a relation between the page faults and number of frames. So as we increase the number of frames, the page faults will reduce. Okay, so this is a desirable behavior, so that we can have a optimal number of uh, frames. You can see here the optimal number is once the number of frames is 4, you can see the almost, whether it is 4 or 5 or 6, the number of page faults remains at 4. So we can select a 4 as a optimal number of frames. The first algorithm is first in first out. So first in first out is whichever page is loaded first, that is when a page replacement is required, whichever is loaded first, that will be replaced first. Okay, so it whichever comes the page first, that will be replaced first. That is the first in first out. So we'll take the example. We have the reference string. This is the order in which pages are requested. We have 3 frames. Okay, 3 pages can be in memory at a time per process. So 3 frames means what? We can have a maximum of 3 pages for a particular process. And we will see when we use this algorithm, there are about 9 page faults. We will see that in a okay, here is the, I would say this is a FIFO algorithm. Okay, so this is the reference string. So what is the technique used here? First in first out. So this is first in first out. Now initially this is the reference string, and initially all the frames are empty. When we get a request for the page 1 will be loaded because there is no need for any replacement. Then we get a request for the page 2. We have one more frame free, so 1 and 2 will be occupied. We get one more request, that is page number 3. So we will have 1, 2 and 3. Okay, now with the first 3 page request, because frames are only 3, 1 2 3 3 frames are there. Now with the first 3 page request, our frames are full. Now there is no free frame. Next is page 4 is requested. When 4 is requested, out of these 3, one has to be replaced. How we decide which one has to be replaced? Whichever came first should be replaced. And you can see here which one came first. 1 came first, then 2 and then 3. So the new page that is requested will be loaded. It will be replaced on the frame where there is a page number 1. So we replace this as 4, and remaining frames will be having page 2 and 3. Right, now again there is a request for the page 1. Right, when there is a request for the page 1, again this is a page fault. So whenever we have to load a particular page from the disk, that is a page fault. So because it is not available in the main memory, so again there is a page fault. Now which one is the came first among these 3, whether 4 came first, 2 came first or 3? So if you see here, next one is the 2 came before 3 and 4. So the next page would be replaced, that would be selected. 2 will be selected as a victim page, then other 2 will remain same. This would be 4 and this would be 3. Now after 1, again 2 is requested. Right, when 2 is requested, from the table among 4 1 3, which one came first? 3 came first. So this will be replaced, and other 2 pages will remain as is, 4 and 1. Now after now 2, we got a request for 5. So if you see, among 4 1 2, which one came, 2 just came, okay, 1 came in the previous swap, okay, and 4 came much before than 1 and 2. So 4 will be replaced with the page 5 and remaining will remain same 1 2. Now what happens is, after 5 we get a request for the page 1. So it is not a page fault because 1 is already available in the main memory, so it will directly reference. After that we get 2, okay, 2 is also, it is not a page fault, 2 is also available in the memory, so it will be accessed from the memory. Then we get a request for 3, right, page 3. So 3 is not available, so it is a page fault. Among these 3, which one came first? The 1 came first, so page number 1 will be replaced with 3, and this would be 5, this would be 2, that will remain same. Next, after 3 we got a request for the page 4, right, page 4. Page 4 is not available here. Among these 3, which one came first? 2 came first, so that will be replaced. Page 2 will be replaced with 4, this will remain 3, and this will remain 5. And what is the last page request? 5. 5 is not a page fault because it is on the memory. So if you see this, how many page faults we got? Page fault is when we don't find that particular page on the memory, that is a page fault. 1 2 3 4 5 6 7 8 9. So we got a total of 9 page faults. And what is the intention of our algorithm? Algorithm should have as minimal number of faults as possible. So with the 3 frames we will have a 9 page faults, okay. And if we increase the 4 frame size to 4, so instead of 3 frames we will have one more extra 4 frames. If we work out this on the same reference string, we will get a 10 page faults. So this is not a desirable. So as we had seen in the earlier graph, as the number of frames increases, the page fault should reduce, isn't it? But there are some algorithm which has a problem with that it will with the increase in the number of frames, the page faults might increase, okay, and that is called as a Belady's anomaly. So Belady's anomaly is what? Even though there is an increase in the number of frames, the number of page faults should decrease, but rather it will increase. So that is called as a Belady's anomaly. And this is another example for the FIFO page replacement. So you can just take this is the already how it works, and you can try to solve on your own. So here just I will give the explanation for the few of the processes, then you will understand the rest. So initially there is this is the reference string that is selected, and initially there is a page request for 7. Initially all the frames are empty, 3 frames are there empty, 7 would be loaded, page fault. Second, 0, it is not in the memory, so it will be loaded from the disk. Then 1, it will be loaded onto the frame. So initially 3 requests, we have 3 frames empty, 701. Now there is a request for page 2, which is the first came among these 3, 701, 7 came first, so that will be replaced with 2. Next there is a page request for 0. 0 is already available in the memory, so it is not a page fault, so it will be accessed from the memory. Then we get a request for the page 3. When we get the request for the page 3, among these 3, which one came first? Page 0 came first, that will be replaced, and so on. See, this is the representation of the Belady's anomaly. you can see from here when no, the trend is like when you increase the number of frames, the number of page faults should decrease. But for certain cases, you can see at when the number of frames are 3, page faults are around 9, and when it is 4, the page faults are 10. So this is the anomaly. So we don't desire this kind of a behavior for the any algorithm. Next one is the optimal algorithm. So optimal algorithm, what it uses, replace page that will not be used for the longest period of time. Means in this particular algorithm we are going to select a process which will not be used for the longer period. Okay, so that is the technique. We will take with the example. Our reference string is same, and we are going to have 4 frames. So this is optimal algorithm. This is the reference strings we have. So initially all the frames are empty, and we have a request for 1 2 3 4. So since we have 4 frames here, the first request will go here 1, then 1 and 2, then 1 2 and 3, and next one is 1 2 3 and 4. Okay, now the first 4 page requests are they are loaded from the disk. All these are page faults because they are not in the main memory, and they are loaded from the main memory, and there is no issue of selecting a particular page because there were free frames. Now after 4, there is a requirement, there is no free frames. Now after 4, what is requested? Page 1 is requested. So it is 1 is already on the frame, it is not a page fault, it will be accessed from the memory. Then page 2 is accessed, requested, that is also not a page fault, it is available in the main memory, and it will be used. Then 5 page number 5 is requested. Now that 5 is not available on the main memory, and this is a page fault. Now we have to replace one of the pages from these frames. So which one is selected? We are going to select which is not used for the longer period. So you can see here 5 is here, that is the one requested. And if you see in the future, we are going to need 1 immediately, 2 we are going to need, 3 we are going to need, 4 is the not required in the near future. We are going to require 1 2 3 but not 4. So whichever is not required in the near future, that will be replaced first. So the page 4 is replaced with the 5, and other pages are kept as is. So we will have 1 2 3 and 5. Okay, and after that, after 5 we have a request for 1. It is not a page fault, it is available in the memory. Then there is a request for 2, which is also not a page fault because it's available in the memory. Then 3 is requested. 3 is not a page fault, it is available on the memory. Then there is a request for the page 4. When page 4 is requested, it is not available on the memory, and it is a page fault. When it's a page fault, we have to replace one of the pages among these 4. How it is selected? If you see the future, 5 is required, so 5 will not be replaced. Now since this reference string ends here, we among 1 2 3 we can replace any page. When the question is any page, we will select the first one which is loaded onto the memory. So it is replaced, the page 1 is replaced with 5. So maybe we can have a FIFO algorithm when there is no more request. Okay, then 5, 2, 3 and sorry, 4 is the next request. 4, 2, 3 and 5. Okay, that is how this 4, and after that there is a request for the page 5 which is already in the memory, so that is not a page fault. Now you can see how many page faults we got. 1, 2, 3, 4, 5, 6. In the earlier FIFO we got 9 page faults. So with optimal algorithm the number of page fault reduced. When we reduce the number of page faults, the performance of the process execution is much faster. Okay, so we get only 6 page faults. Next, the question is, how do we know the biggest problem with the optimal algorithm is how do we know which are the processes that which are the pages that are going to be requested in the future. So that is impossible to know which are the pages that are going to be requested in the future. So right now this is we worked on a reference string, and here we very well know what is the future request of the pages, and accordingly the optimal algorithm works. So optimal algorithm, this is it is not possible to implement this algorithm, but this algorithm is the best algorithm that can be used for the analysis purpose. Let's say we have a algorithm. For the evaluation of the algorithm we can use the optimal algorithm as a benchmark. So the best algorithm that we can design and implement, its performance can be compared with the optimal algorithm, but implementation of the optimal algorithm is not possible because of the reason we will not know how the future request of the pages will come, and that is very difficult to get that information. To get that information, it is very difficult. So that is the reason it is not possible to implement this particular algorithm used for measuring how well your algorithm performs. So we can use it as a for the evaluation of the other algorithms with this as a benchmark. This is one more example. So reference string is 70120. So again here it says whichever process which is not required in the future for a very long time, that page would be replaced. That is the technique that is used here. So initially we have 3 frames. 701 is loaded. Okay, 701 is loaded, and then there is a request for the page 2. Among these 3, okay, which one is not needed in the near future? So if you see here, 7 is not needed until like almost this would be like around 18th or request. So we don't need 7, page number 7 in the near future, but 0 and 1 you can see 0 is requested here, 1 is requested here. Among these 3, 7 is the one which is not required in the near future, so that particular page will be replaced. 201, then we get a request for the 0, not a page fault, it is in the memory. Then we get a request for 3. When we are replacing with a 3, it will what are the available processes? It can replace 2, 0 or 1, but if you see the in the near future, 0 is requested here, 2 is requested, again 0, 2 is there, 1 is the which is least requested in the future, so that will be replaced. So that is how this algorithm works. Next, to have a different flavor of the optimal algorithm, we can have recently used LRU algorithm. In case of an optimal algorithm, it is looking into the future usage of the future request of the pages. In case of a least recently used algorithm, it goes checks the a history, or it is a backward lookup, okay, how pages are requested. So whichever is a least recently used, that particular process will be used for the replacement. Means what? If a particular page is requested in the near future, we are not going to replace that. The page, let's say it was requested long back and it is not requested again, that is the candidate for the page replacement. Whichever is least recently used, that means we are going to keep the most recently used pages, and we will replace the least recently used pages. That is the technique that is used in the LRU algorithm. This is the same reference string. We will go back to here. We will have one more. This is LRU. I will say this is LRU algorithm. Least recently used. This is the reference string, and we have 4 frames. 1, 2, 3, 4. 4 frames are there. The first page will be loaded like this. The second page request will be loaded like that. Third page request will be loaded like that, and fourth page request would be loaded like 1, 2, 3, 4. Now all the frames are full. Then there is a request for the page 1. It is not a page fault because it's already available. 2, not a page fault, already available in the memory, not a page fault. Then there is a request for 5. So 5 is not available, so it's a page fault. We have to replace one of these. So how we are going to replace? We are going to replace which is least recently used. And how do we find least recently used? What you have to do is you have to take, so this is the requested page. Look on the left hand side, so that will give us the least recently used. So if I go to the 1 left to the 5, 2 is the most recently used, next 1 is the, compared to this, this is the second most recently used, this is third most recently used, and so on. So I have most recently used is a 2, next is 1, okay, next is 4, next is 3. So among these 4 processes, you can see 3 is the least recently used. So that is the page, victim page, that is selected, and it is replaced with page 5, rest being the same. We will have 1, 2 and 4. Now next one is the request for the page 1. There is no change because this is not a page fault, it is available in the memory. Then 2 is requested, 2 is available on the memory. Then 3 is requested, 3 is not available on the memory, so 3 results in a page fault. Again the same technique, least recently used among 1, 2, 5, 4. So if you go to the left, 2 is most recently used, 1 is also most recently used, and 5 is also most recently used. 2 is already we considered most recently used, 1 is also considered here. Then 4, among these 4 is the least recently used, so that particular page 4 will be replaced with 3, and remaining will remain same. So 1, 2, 5, 3. Now after 3, which is the next page requested, 4. Now among these 1, 2, 5, 3, which is least recently used, 3 is the most recently used, 2, 1, 5. We can see 5 is the least recently used, so 5 is replaced with 4. So we will have 4 here, this is 1, this is 2, and this is 3. Now next is there is a page request for 5. If you go to the left, 4 is the most recently used, 3, 2, 1. Among all these, 1 is the least recently used. We will have page 1 is replaced with 5, 5, 2, 4 and 3. Okay, so how many page faults we got? 1, 2, 3, 4, 5, 6, 7, 8. So if you see LRU algorithm, it is not as good as the optimal algorithm. because optimal algorithm gave us about 6 page faults, and but it is better compared to the FIFO algorithm. FIFO algorithm we had a 9 page faults, here we have 8 page faults. So compare it to FIFO, this is a better algorithm. How do the implementation using a counter implementation to find least recently used. Every page entry has a counter. So in the page table we will have one more entry for the counter. Every time page is referenced through this entry, copy the clock into the counter. When page needs to be changed, look at the counters to determine which are to change. Okay. So in this particular algorithm we need to find which is the least recently used. So for that we need to have one more additional attribute, using a counter we can implement, so that we can copy what is the time, okay, what time it got into, so we will know which one is the least recently used. This is the another example. This is the string and LRU. First 3 page request will be loaded onto the free frames 701. Next we have 2. When we are selecting replacement of 2, we will check the most recently used is 1 and 7 is the least recently used. So it will 7 will be replaced with 201. Then request is for the 0 page. 0 is already on the memory, it is not a page fault. Then 3 is requested. 3 is not available on the memory, it's a page fault. 0 is the most recently used. 1 is the least recently used. So this 3, page 1 will be replaced with 3, 203 and so on. LRU algorithm, in case of a LRU algorithm, stack implementation. So either we can have a counter implementation, we can use a counter, and we can have the clock copied onto the counter when we load the page in the page table, or we can use a stack. Keep a stack of page numbers in a double link form. So we can have a stack with the most recent access of the pages, then using that particular stack we can will come to know which is the most recently used and which is the least recently used pages. Page referenced, move it to the top. Okay, as we reference any page, it will go to the top. So one disadvantage is 6 pointers to be changed, because any time we have a page request, then that stack, if it is in between, then we have to bring it to the top and readjust the other values. So that will requires a change. No search for replacement. So the biggest advantage compared to the counter, in case of a counter we have to go through the page table in order to find based on the time which is the least recently used. So we have to do a search. In the case of a stack, it's very easy. If you go to the bottom of the stack, that is the least recently used process, we will directly get, there is no search involved. In that way, if we have stack, that would be much faster. There is a least search or no search required. So you can see this is an example of a stack, use of a stack to record the most recent page references. So this is the stack and this is the reference string. Now this is the stack status before A, and before A you can see 2 is the most recently, so it is top on the stack before A. So this is the stack, 2 is the most recently, 1 is next, then 0 is next, 7 is next, and 4 is last. So the most recently used is on the top and least recently used is on the bottom. Then there is a request for page 7. When the page 7 is requested, 7 will becomes the most recently used page. So 7 will go from here, it will go to the top. So you can see here 7 goes to the top, and all these values they will get pushed down. So 7, then we will have 2 1, and this 7 is replaced with the 0. So this is how the stack will change after reference of the 7. So you can see at the bottom, whenever we want to have a page replacement, we can easily find whichever is in the bottom of the rack, and if it is available on the frame, that is the page that will be selected as a victim for the replacement, page replacement. LRU approximation algorithms. So there is the LRU algorithm has been announced as a LRU approximation algorithm. In this case, we can use a reference bit. Okay, when each page associate a bit in the page table, along with each page there is a one reference bit will be stored. When page is referenced, that particular page is set as 1. Replace the 1 which is 0. If 1 exists, we do not know the order, however. Okay, so in this case what we are doing, in order to have a better LRU implementation, we will use one more bit called as a reference bit, and whenever there is a page access, we are going to store that bit. Whenever there is access to the page, we are going to store as 1. Now when we are searching for the least recently used, along with that we will check the reference bit also. If the reference bit is 1, means that even though it is least recently used, and if the reference bit is 1, that means this page is accessed. Then based on that we can select or not select. If there is a page with a 0 reference, then we can select that particular page for the replacement. And similarly, there is a second chance. In case of a second chance, we need again a reference bit, and this most of the time this reference bit is supported as a hardware, and that hardware support is given by the operating system. In case of a second bit, a reference bit, again a reference bit is used, and if page to be replaced has a reference bit is equal to 0, then set reference bit as 0. So we give a second chance. What we will do is, we don't, if the bit is 1, we won't replace it, rather we give it a second chance by making that reference bit as a 0. So then we will select the next page which has a reference bit as 0. Okay, so the reference bit will be every page will be given with one more chance if reference bit is set to 1. And how it is given a second chance is, whenever it accesses that particular page, when it is given with a second chance, the reference bit will be changed from 1 to 0. When replacement algorithm runs again, when it comes for the second time and it finds the reference bit as 0, that particular page will be replaced. Okay, set reference bit to 0, leave page in memory. We will not replace that. Replace next page, okay, in a clock order subject to same rules. Same rules means, if it is 1, give it one more chance. If it is 0, then you select that particular page for the replacement. So that is the same thing. You can see it from the diagram. Okay, counting algorithm. In this particular algorithm, what we are going to do is keep a counter of the number of references that have been made to each page. So we will have a counter which will count the references, how many times a particular page has been referenced. So that number will be stored in a counter, and that counter is used for the that counter is used by the algorithm to select the victim page for the replacement. For example, we can use a LFU algorithm, least frequently used algorithm, or MFU, most frequently used algorithm. In case of a least frequently used algorithm, we can have the counter, right? The counter shows how many times the particular page is referenced, and let us say one particular page has a count of 2 and another page has a count of 10. The page which is having the count of 2 is the least frequently used, so we can select that particular page for the page replacement. Whenever we have a new page request, we can use that particular page for the page replacement. So LFU algorithm replaces page with the smallest count. However, there is a drawback with the LFU. Let us say there are certain pages which are extensively used in the initial stages of the program. Then what will happen is those particular pages will have a high numbers, and later in the program, if those pages are not referenced, right, then those pages will remain on the memory. Even though they are not referenced, they will remain on the memory. That is one drawback here, and we can use some aging technique for to solve that problem. Whenever it is not referenced, say based on whatever criteria, we can age it, we can decrease the number. So LFU algorithm, what it chooses the page with the smallest count for the replacement. Counter to LFU is the MFU, most frequently used algorithm. So in this case, what we do is we replace the page which is most frequently used. Here the idea is the most frequently used algorithm is the one which has been used many times, and the pages which are having lower number are yet to be used. So that is the concept here. So based on the argument that page with the smallest count was probably just brought in and has yet to be used, means the process which is having a smaller count, it will be used in the future because it has just brought into the memory. That is the concept in MFU algorithm.